Okay, so we've talked about how floating point works. We talked about the hardware. We talked about how it looks like in assembly. There's a couple of other gotchas you need to learn to really understand floating point and why it's so dangerous, in case you didn't know that already. So the next set comes out with how do you do rounding, and there's actually rounding control. Now, y'all probably used to some rounding. There's truncating, there's rounding, there's always round or the standard round that you're used to. And there's different extra bits of precision in order to deal with that type of rounding. We call it guard, round, and sticky. Those are the names for now. We'll get to it in a moment. Not all floating point units implement all options. Most programming languages and libraries just use the defaults, and that's okay. It's a trade-off, of course, of which ones are used. All right. Are we really not going to go into it?
Wow.
Those lame slides.
That's not
All right.
Wow.
All right, well, I guess not.
I guess we don't need to know it.
Mm-hmm. All right, subword parallelism. This is used everywhere nowadays. The classic examples with graphics and audio, you can take advantage of simultaneous operations in short vectors. For example, 16 8-bit adds. Woo. Huh. All right, 8-bit adds, you can do 8 16-bit adds or 4 32-bit adds if you have a 128-bit adder. Why is this useful? For every 32-bit, that can represent a pixel on the screen, red, green, blue, alpha. So if you need to do a transform on the entire screen, it would be nice if you just have one operation that does all your pixels. That would be a pretty wide vector, but even if you had an instruction that would do 4 of them in parallel as opposed to 1, that's a speed up of 4, technically, on that one operation. So this is called data level parallelism, because instead of trying to execute multiple instructions at the same time, you just have one instruction that operates on multiple pieces of data at the same time. And that's what I think is most intuitive. You know, don't do just one add, do 4 adds. Make sense?
Yeah.
Don't do 1 multiplication, do 4 multiplications, right?
Right.
I like the pixel example.
Well, it's just, but basically, we're pipelining it.
No, there's no pipeline here.
We have 4 different hardwares. Oh,
You-
no,
you
never mind.
have
We don't know since we're doing the
128
bits.
bit
Never
added.
mind.
This is gonna.
Yeah,
You
okay.
just chop it up so you're actually doing 4 32-bit adds.
Right. Okay.
That's all. This is also called data level parallelism, vector parallelism, or the better word is SIMD, single instruction, multiple data. You have one instruction, aka one 28-bit add, and you're doing it on multiple pieces of data. This is opposed to what we've been doing beforehand with this single instruction, single data. You have one add, you do one add on 2 pieces of data, and it goes back into 1. SysD. Yep. SysD.
This is deep. How much money did you have? This is deep.
All right.
60.
So how did this happen? How do we implement this
How
in
did this happen?
in x86? Because originally processors did not have floating point. They came up with the 8087 coprocessor. What would it have? 80-bit extended precision registers. Oh, great. Used to push down stack, which is even more confusing. And FP values are 32-bit or 64-bit in memory, converted with load store. Very difficult to generate, optimize the code, and poor FP performance. Basically, hey, we have a piece of hardware. Oh, it doesn't work. And worked very well.
Nice.
We could go through this, but I see absolutely no reason to.
Not our job.
Good.
Not my job.
So after that, by the way, the 8087 came out, I want to say early 80s. It's been a while. They decided to update it and come up with something called SSE. Have you all heard of that one before? SSE instructions, extensions? Nope.
Nope.
Nope. All right. Extended 8-bit registers in the basically the 64-bit instruction set architecture. It adds 4 128-bit registers, so you can do 2 double precisions or 4 single precision, and it just allows you to operate on them simultaneously. It is extended to something that actually makes sense, aka what we learned today. Okay, matrix multiply. Whoa. Oh, okay. Unoptimized code. This hopefully looks very similar to beforehand. We're going to skip a bit. Wow. We might skip a lot. Yeah, we're going to skip a lot.
Yay.
Good. Excellent.
You're done.
If you want to look at the assembly, which I do, which does, the key points here of the assembly, let's go ahead and at least look at that. Notice that it's going to pull in the register, and then it's going to do a broadcast of basically multiple multiplications at the same time, and do another parallel add at the same time. It's basically, you have to send it its offset of where the numbers begin, and then you can do the adds and the multiplication. But it takes a little more time to set it up. That's all that's going on here. Okay, what's this? Shift and division. I don't know why they didn't tell you this earlier. Remember that SLL where we're doing shifting?
Yeah.
So shifting to the left always multiplies it by 2 to the I, whatever number you supplied. Shifting to the right is essentially dividing by 2.
Divided by 2 the number of times you shift.
Yeah, number 2 times shift, divided by 2 to the I.
Okay.
Works well for unsigned integers. If they're signed, things can be kind of weird. But for your hardware, you just replicate the sign bit. So if you're downshifting by 2, have y'all done this in C? That's how you do downshift.
Nope.
Unless you taught it.
At the end of C. Well back, I thought we were.
All right, so this is downshifting by 2. So
Good to know.
32 to 2 is going to equal 8. Yep. So what's 2? Oh, I'll do 4 because I wrote that instead.
64.
Yep.
You just multiply it.
2 to the 2 is 4, so it's 4 times 30, or I'm sorry, 4. 32 divided by 4 is 8. Right. 3 to the third is 8 times 4 because you're upshifting is 64. But you're really, all you're doing is you're shifting the bits. because you-
Wait.
4
2 to
times
the 3
8.
is 8. 8 times 4 is not 64, it's 32.
Oh, you're right.
Okay.
Arithmetic, silly arithmetic. All right.
You don't need it.
Oh, well, it's not
To use that
important
computer.
for
I'll never use it in
everything.
real life.
Whatever. Okay. But all you're doing is you're shifting the bits, the bit representation, because that's how we represent numbers on a computer. So shifting digits up and down is a lot easier than trying to do the multiplication.
How important would you say it is to know C code? Because I don't know if I've ever coded in C. Never.
You've done C++, right?
Yeah.
Yeah, it's just remove the STL and classes. Now you have C. Everything else is the same. 99% of everything else is the same. There's a couple of gotchas, but not too many. Use malloc instead of new. Is really the only big difference. There's a couple other minor things.
So I like C++, and we're taught C++, but every teacher who teaches C++ always seems to refer, and you're like, well, you're giving me code in C. Every teacher.
I don't like C++.
Oh,
Really?
well, at least up front.
What do you like C?
What do you like?
Oh, do I like C? No.
When given the choice, C++ or Java?
What's your
C++ is
favorite
Do
language?
I put my finger in the top socket or the bottom socket? You just
Then
have-
why do you teach us those languages?
Wait, but why do you prefer C if you said it's just like C, but 99?
Well, no, C.
All right, so 2 reasons.
Alright.
One reason, I prefer the problems that C has to solve. I prefer low-level, kernel-level problems that C addresses. You do not write those in Java, or if you do, you're not going to be around for very long. The reason, so that's why I prefer C instinctively. Why I don't like C++ or Java, while I understand the benefits of OOP, people have abused it to the extreme to where it's become a disease. It's now a virus just
What's your
infected.
favorite language?
Favorite language? It's
Like if you're just gonna work on a project of your own choosing.
so again, You asked me the wrong question. I like the problems C solves, so I usually like coding in C because of the problem I'm solving.
If you were doing a senior project, what would you write it in?
It depends on the project.
Oh,
If you're creating an app.
The language is a tool.
Yeah.
It's just a tool.
that makes sense.
You know?
And depending on what the project is,
Yeah.
it's the tool.
Yeah, you just need to find the right
I
tool
gotta
for the
figure out
project.
tool.
Some tools are sharper than others. You gotta
Some,
be
well, it
careful that
depends on what you
cut
want to do,
yourself,
right? If you're just doing a hammer, I mean, a nail, you need the finesse of a hammer. But you know, if you're
But
trying
You
to,
don't need a. You
but
don't
if you're
need
trying
a
to drive
handsaw.
in, you know, a steak or something, you're right. You're going to need something bigger. You're not
A
going to.
mallet.
Yeah, a mallet. You know, it's not going to work.
Yeah, you're not gonna use a handsaw on a nail.
Right. You're not going to try and hit the nail with a screwdriver.
I mean, you could try.
Now, I've
You're not
met
gonna
peop-
use a lawnmower on a nail.
Right. Now, I've seen people use a hammer on a screw before. That always ends poorly. But yeah, you don't want
You
to.
can use a
You don't-
screwdriver on a nail more easily than you can use a hammer
But that's
on a nail.
my example of why I don't like OOP. They're using a hammer when you have a screw.
That's disgusting.
You can do it. I've seen it done. It kind of works.
Kind of.
All right. Well, that was a great sidetrack.
Squirrel.
Squirrel. All right. Notice if we're downshifting by 2, you just take whatever the significant bit is and you keep replicating it, and that'll give you the correct answer due to 2's complement. Or you can do with 3 of these guys, which is mean. Oh wow, that's not good. Which means you don't do the sign extent. That's the only difference between the 3. I don't know. I've never seen this used.
Awesome.
Okay.
Ignore.
But if you see the 3, know that something weird's going on.
Awesome.
Nice.
All right, associativity.
Oh, no.
This is my favorite example of why floating point is terrible.
Oh joy.
In case you haven't been convinced yet, by the way, floating point is very important, and I'm glad we use it. But this is where it becomes very troublesome. Oh, that was
He's
beautiful.
just repeating.
Yeah, you should say what you're saying.
I know, it's amazing. All right. So we're doing x plus y plus z. And over here you have x plus, of course, y plus z. The 2 should produce the same answer, correct? Mathematically, the 2
Yes.
are the exact same.
Sure.
But depending on depending on how you implement it with floating point, they are going to produce different answers.
Gross.
Exactly.
You're
That is
gross.
dumb.
What?
And is this where we come to the standardization of how we do things, or standard?
No, this is floating point, period.
Period.
This is, you gotta be careful. So if you do x plus y, notice that x and y are large numbers, well, large number. Largest or small, but they're negative, so they would cancel to 0 if you added them. And then you add 1, you get 1.0. All right, makes sense. That's what we wanted to do. On the other hand, if we did y plus z first, where we took 1.5 plus 1, we're going to get the same number back because 1, we've lost that precision because it's so far down the line we can't capture it within our floating point digits. So the 1 is ignored. Then when you add that negative number back to it, you get back 0. Same formula, different answer.
Gross.
That would suck.
Yes.
Don't do floating point.
Well, no. You have to do floating point in certain situations.
Just try not to do associativity.
You have to be careful when you're doing it about your magnitudes.
Because 1 is so insignificant to that number.
Compared to 1.5, yeah, e to the
Even if you add 1 and then subtract the number back, you're still going to, it's going to be negligible. You're going to get 0.
yeah, you're gonna get 0 because there's no way to capture that 1 in the precision.
So is there, so you would want, if you're doing associativity, you'd want the magnitudes to be as close together as possible for each association.
The way you really do this is you find out what your magnitudes are, and then you have a delta, such that if the number is less than your delta, you just consider it 0. So for example, these are 10 to the 38, so your delta might be, let's say you're doing a floating point, so you only have 6 digits, so your delta is 10 to the 30th. So if your answer is less than that delta, answer equals 0. Because for all intents and purposes it is. So you do this, normally you do this check after you have this answer to force it to be 0 if it's within some delta or some precision.
So both answers will be forced to be 0 in
Yeah.
this case.
Yeah, they were both, because 0 is less than 10 to the 30th, and so is 1. Your answer's 0. That is the way you're supposed to do it. But you have to keep your track of that delta no matter what you're doing. We just call it a delta. It's really, once it gets below a threshold, we just consider it 0.
It's so tiny.
Okay, who cares about the accuracy? Well, we just showed you how it could be bad here. There is everyday customer. My bank account is out by 0.002 cents. That'd be kind of weird, right? You're using the floating point for banks, and you're off by that much cents?
Did you hear about that guy that was doing that?
Oh, you like in Superman 3?
What do you mean? Wait, what?
What?
Just stealing the fractions off of every transaction?
Yeah.
Yeah. Yeah, just like in Superman 3, right?
Oh, I don't know.
Superman 3.
I've seen like the first two.
They did that in Office Space, I know.
Right.
Yeah.
Oh, so now I need to say just like in Office Space.
Which one is
I
it?
see. So I got to upgrade my
Yeah.
my movie references. I see
Yeah.
how it is.
Because those Superman movies are.
Is that the first
Those are
Superman?
very old.
1970s?
And they're terrible movies.
The first one was 78, and the other one was early 80s.
I was actually
So
gonna
we're
say
talking about
78.
early movies.
Didn't that actor die by like breaking his neck in a bull riding?
Yeah.
Christopher Reeve,
Well, no,
yes.
riding.
No, he got
riding a
paralyzed.
horse.
Yeah,
Yeah.
he was
Yeah.
paralyzed, yeah.
Horse riding.
Yeah,
Yellow horse.
Superman's supposed to be the Man of Steel.
I don't know.
Oh,
I'm
yeah,
not,
body
I'm not Gene Hackman.
right.
You can't.
Yeah, that was pretty good.
Happens to-
All right.
You can stop
Well,
the
what
scene.
happened also is the Intel Pentium processors actually had a floating point division bug where it literally did not do division correctly.
Oh, another bug.
Yeah, I know.
Intel has some problems.
Not as cracked up as they make themselves seem.
So, well, here's the problem. So Pentiums were doing incorrect division and floating point. What do you do? What do you do in that situation, Kalia? Your processor is wrong.
Replace the processor.
Hope nobody realizes and
Oh, they did. Oh, they did.
Comes the money.
They had examples of they're like doing a spreadsheet calculation, and it was like, this is obviously the wrong answer in my spreadsheet. Yeah, they'd write a program. This is obviously the wrong answer.
Okay, if you can't get it right in a spreadsheet, there's a problem.
No, that's-
Right. Well, it's because your hardware's wrong.
Yeah.
Yeah.
So,
You can't fix that with software. You can try.
well, you just don't do floating point hardware anymore, right? So everything we just did, we have to write in software.
Just don't do what you wanted to do with it.
That's
Yeah.
dumb.
Yeah, it's terrible. So Intel had to replace all those chips,
Of course.
which was not cheap. But they still have a ton of money, so they're winning. And of course, now we have Meltdown and Spectre, which is classic. All right.
Classic Intel.
Concluding.
Out of the whole lecture, we just got concluding.
It was almost like she was stranded on a desert island and saw a boat. Civilization.
Wow. All right, bits have no inherent meaning. Do you understand what that means? They're just bits.
You have no meaning.
But what does that mean?
The bits don't represent anything until we
Give them something.
something to represent, right? So they only represent what we tell them to. Depends on the instructions. Computers' representations of numbers, finite range of precision. No need to account for this in programs because your compiler is going to take care of everything for you. And now C is a very nice language. Yeah, one thing to keep in mind is as an architect, C is an extremely high-level language.
Whoa.
Whoa. Your instruction set architectures support arithmetic, signed and unsigned. You get bounded range and precision for floating point. The MIPS ISA has a lot of has instructions. Oh yeah, this is important nugget.
Nugget.
Nugget. You have hundreds of instructions, possibly 1,000 in MIPS, but 54 instructions represent the vast majority of what occurs. The end.
Hallelujah.
Wow. Any other questions?
Actually, that statement actually does, it's a good advertising for MIPS, period. That 54 most frequently used, that's good.
Yeah. All right. Any other questions?
Can you take a nap?
Does Kai have a question for us?
No, I do have a question about the homework.
Okay, we'll get to that. All right, that's all for today. We got lab time and then chapel. What?